So today I want to continue our conversation about analytic geometry and those getting you ready skills so that you can tackle this new unit. So by now you're aware that any set of parallel lines are going to have the same value for slope. So that is important to know because several times in this unit you'll be asked to find the equation of a line that you see on a graph or that you've created from joining a couple of different coordinates. So for example, I can calculate the slope of this line by looking at any two coordinates on its graph. And I could go through the whole process of using the more complicated formula, slope is equal to delta y over delta x. But for this purpose, I can see very clearly what the slope is using by counting squares. So I'm just going to count my rise and count my run. And it looks like I'm rising 2 and I'm running 3. So that gives me a slope of 2/3. So my first equation, therefore, is going to have a slope of 2/3. And my second equation is going to have a slope of 2/3. Okay, so far that's where I am. But I can also locate the location of the y-intercept for each line. And so the higher of the two lines has that intercept at +2. So now that line is done. And the second of the two lines has an intercept at -1. So I can easily find the equation of lines that are parallel. If I know the slope of one of the lines, then I can easily solve for the y-intercept if I'm given the right information. So conversely, the slope of perpendicular lines, and let me remind you all what we mean by perpendicular lines. Those are lines that not only intersect, but they intersect at a right angle. Okay, so you may remember this from grade 9. It is a topic that you did cover, but you may have forgotten it. But they are related, and so it's good to know that they're related, because if I know the slope of one line, then a line perpendicular to it I can easily retrieve if I know also another point on that line. So the slopes of perpendicular lines, we say, are negative let's see if you can finish this sentence, reciprocals of each other. And so I'm going to talk a little bit more about what that means. Let's just get the equations of the lines out here, and then maybe we can remind ourselves what the heck that means. So I'm going to focus on, I'm going to call this line number 1. And I'm going to call this line number 2. And so if I want to find the slope of this line, I'm going to locate my y-intercept. And then I'm going to find another point on the line over here. I'm going to choose this one right here. And it looks like when I analyze it, I'm rising 1 and I'm running 1, 2, 3, 4. So I can say that the equation of line number 1 is y equals 1/4 x minus 2. So that's 1/4. And then I look at the second line. Its y-intercept is 1. But I'm going to also look at its slope. So I'm going to pick another coordinate. Here's my slope here, or my other coordinate rather. It looks like I'm going up 1, 2, 3, 4, and back 1. So that means that my slope, so let's look at that. I'm going up 4 and back 1. So my slope is really -4. So let me write that in. So y is equal to -4x and then +1. So now I have my two lines. So let me take a look at that. So here are my two slopes. Here we go. And so how are they related? Well, they're negative reciprocals of each other. If you look at these, what do you see? Well, if I were to take the slope of my first line and invert it or flip it, I would end up with 4/1. And then, so that's the reciprocal part. The negative is that I take what I get when I flip that and I give it a negative sign. So there you can see how they're related. So here it is in words. So to find the negative reciprocal of a number, we're going to invert the fraction, and then change the sign. So let's go through a few examples to remind you about how to do this. So if I were to look at this at 2/3, let's start with 2/3. What I need to do first is I need to flip that fraction upside down. And so when I do that, I get 3/2. And so I'm partly there. But now I need to change the sign. So since, even though it's not written, this 2/3 is positive, when I flip it, I need to make the value negative. So now I've taken the negative reciprocal of that value. So the slope of a line with 2/3 would be perpendicular to a line with a slope of negative 3/2. So let's carry on. So maybe you want to pause the video and try the next two examples. I've got two more here. And then resume when you're ready. All right, so when I look at the first example here, I see that -8 isn't really a fraction, so what to do about that? Well, you'll remember that I can make any number a fraction by putting it over 1, creating a denominator of 1. And so now I'm ready to flip that upside down, and when I flip that upside down, I get -1/8. But you'll remember that I also need to change the sign, and so I'm going to take that negative and make it a positive now, right? So really, I have 1/8. All right, let's try that second example now, or our third example rather. So I'm going to take this fraction, I'm going to flip it upside down, and that will give me 4/1, -4/1. But I want to change the sign, so because it's negative, it now becomes a positive. And I really don't need to write a number as a fraction over 1 if the denominator is 1, so my slope is simply 4. So I hope that you did okay with that. I'm going to carry on with another topic soon. However, there are some homework questions from your textbook that I'd like you to work on. I don't have them here. Let's try another few examples first before we get on to the homework bit. So here's example number 1. So in this example, I'm saying find an equation for a line that is parallel to the line y equals -2x plus 5 and passes through the point A16. All right, so I'm going to highlight this bit about it being parallel because that's important. So as soon as I know that the lines are parallel, I know that the slope is going to be the same for these two lines. So I can right away go and write out that my equation of my line is going to have, if it's in the form y equals mx plus b, I know that now the slope of my line is going to be -2. So I just noticed that the mute was on for the last little bit of this. I'm hoping that you saw my solution and were able to make sense of it. But please put a star beside it if you have any questions about what it is that I've done, and I'll be happy to help you out. So in this second example, I'm finding a line that is not parallel to, but is perpendicular to the line in question. And so then I have a little bit more work to do because I need to discover what the slope is. So if the slope of my original line is -1/2, then I know the slope of my new line has to be the negative reciprocal. Okay, so let's go about working that out, right? So if the slope of my first line is -1/2, I'm going to symbolize the slope of my perpendicular line. I didn't really draw that very well. Let me do that again. You can show that lines are perpendicular by drawing that. Sort of a line with a line that's at 90 degrees to it. So my perpendicular slope would be the negative reciprocal of that value. So I'm going to flip my fraction upside down, and I'm going to change the sign. So because my 1/2 was negative, my new slope is positive 2/1, or simply 2. So my new slope, the perpendicular slope, is 2. So now I'm ready to keep going. So I'm going to, I know that I need to insert that slope into my y equals mx plus b form. So I'm going to go ahead and do that. So 2x plus b. And again, I'm going to go ahead and I'm going to use the fact that I have this coordinate 4 and -9 to solve for b, just as I did in the last question. So oopsies, let me switch to a better pen. So -9 is equal to 2 times 4 plus b. Let's clean this up. -9 is equal to 8 plus b. So b is equal to -9 minus 8. So that gives me -17, which is a large y-intercept. But anyways, here we go. So I'm almost done. All I need to do now is sub that value for the y-intercept back into the original equation. Y equals 2x minus 17. And now my equation is done. So now's the time for homework. Here are some homework. There's a homework question for you to take a look at. And if you need additional practice, I'm thinking I might assign some. So look for that on Google Classroom as an additional post. All right. So the next thing that, it is a geometry unit. And so the two classes of shapes that we're going to be applying some algebra to are triangles and quadrilaterals. So I wanted to go over quickly some of the basic ideas and principles and relationships between triangles, different types of triangles, and also different types of quadrilaterals. So there will be a Kahoot on Monday testing your recollection of some of these principles. So pay attention. So you'll remember that if we look at, classifying triangles by side length, then we can classify as scalene, isosceles, or equilateral. So what do each of those mean? Well, equilateral, I always remember equal. And so what I'm looking for here is a triangle that has equal side lengths. And given that, I'm also going to have equal angles, right? And so you may remember that all of the angles in a triangle will add up to 180 degrees. And so if my triangle sum is 180 degrees, and I have to divide that by 3, that means that each of my angles in here for my equilateral triangle are going to have to be 60 degrees. So that's may come in handy at some point. All right. So another thing I want to mention is that sometimes we symbolize that angles are equal by putting a little dot or a little symbol. And there are other ways that we can depict that as well, and I'm going to carry on by showing you that. An isosceles triangle has 2 side lengths that are equal, and one side length that is not equal to the other. But it's also there's another important property that I want you to know, which is this: the angle opposite those side lengths that are equal are also equal to each other. That was a bit of a mouthful. Let me show that again. So if right here I have an angle or a side length that is equal to this side length, then their opposing angles are also equal to each other. So I can show that in a symbol. In this case, I'm going to show it by using sort of a little dot again. and then a dot, but I'm going to show that this angle up here is at the top vertex makes an angle that is different. So I'm going to use a different symbol. In this case, I'm going to use an X. Now, in a scalene triangle, none of the sides are equal, and therefore none of the angles are equal. So I can symbolize that by, instead of using dots or X's, another way that you will often see that represented is by showing like a little curvy thing. So if I might show one curvy thing here, maybe two here, and maybe three here, in order to indicate that none of those angles are equal. So the next way we can classify triangles is based on their angles as well. So the angle size. So if you have a triangle where all the angles are less than 90 degrees, and you'll remember that a 90-degree angle looks like, the corner of a square, then you call it an acute triangle. If the angle is above, if the angle in a triangle, if one of them is greater than 90 degrees, like we see right here, then we call the triangle an obtuse triangle. Okay, but we're going to remember that all of the angles are still adding up to 180 degrees regardless. Okay, and one of the triangles that we're going to be really concerned about in this unit is the right triangle, and we're going to talk a little bit more about that in our Get Ready skills. But you can see that it has that right angle there. All right, so that's it for triangles. I want to talk next about quadrilaterals. So quadrilaterals. So we're going to see a whole bunch of different quadrilaterals, but what makes them a quadrilateral is the fact that they all have four sides, the whole quad bit, right? So when I look at these, I can see that first of all my trapezium, which I'm not sure if that's a new word, has four sides, but none of them are parallel, and none of them are of equal side length. Incidentally, another property of all quadrilaterals is that the angle sum is 360 degrees. Okay, so you can think of it this way. Really, all that a quadrilateral is a set of two triangles that are joined together. I can kind of separate them. I didn't do a very good job of that right here, but I could separate that into two triangles. And I know that each triangle, it has a triangle sum of 180, and 180 times 2 gives me 360. So that's going to be an important property to remember, perhaps. Okay, next we have the trapezoid. And a trapezoid, we can classify it as a trapezoid because it will have exactly one parallel sides. So when I look at this, I will indicate the parallel sides by drawing these little arrows. Okay, but it has the two other sides are not parallel to each other. A parallelogram, on the other hand, we can tell it's a parallelogram because it will have exactly two pairs of parallel lines. Okay, and so, I'm going to depict the one set of parallel lines like this, and the fact that the other set are parallel to each other, but not parallel to the first set, so I'm going to use two little arrows to depict that difference. That's how I'm going to represent that. Okay, so a rhombus is sort of like a square on a slant. And so it has basically all side lengths that are the same. So this side length is the same as this side length, is the same as this side length, is the same as this side length. In addition to the fact that it has two sets of parallel lines similar to the parallelogram, right? So it's essentially just a parallelogram with all four sides being of equal length. Okay, and so a rectangle, we know, but we can also classify it as a special type of parallelogram where all of the angles are right angles, and the side lengths two of the side lengths are the same, here and here, and the other two sides are not the same, but are the same to each other, but not to the other two sides. Whereas a rectangle is a special type of parallelogram where we have right angles on all four corners, but we also have side lengths that are all equal. So there's your little review. Now, it's also important for you to know that the 360 degrees applies to each and every one of these quadrilaterals. All right, I think we're ready to move on to the next section, but get ready for that Kahoot on Monday morning. All right, so Pythagorean theorem is a concept that we kind of run you through inside and out, I think, in grade 9, if not before grade 9, and that's because it comes up in a whole lot of places in math. Now, we tend to teach you, the formula. Let me get a pen here. We tend to teach you the formula, c squared equals a squared plus b squared, and that's certainly useful, but not all triangles are going to be labeled as A, B, or C. So I think it's more important for you to understand the relationships between the side lengths and their squares. So let's first remember how to find the hypotenuse in a right-angled triangle, because this triangle isn't labeled, or some triangles you might encounter might be labeled with completely different letters or symbols or whatnot. All right, so it's mostly important for you to find the hypotenuse. How do you do that? Well, you locate that right angle, and then you go to the side that's directly opposite it, and that will always be your hypotenuse. So no matter how the triangle is oriented, you find that right angle and you locate the side opposite it, and it will be your hypotenuse. Now, some people will say, well, it's also the longest side, and that is certainly true. It is the longest side on a right triangle. However, that isn't always evident in a diagram, so we need to be cautious of using that approach. All right, so regardless, what is most important when working with Pythagorean theorem is that you have the hypotenuse all on its own on one side of the equation, and then you have the square of the other two sides on the other side of that equal sign. That is what is most important when working through Pythagorean theorem. If you wish, you can label your triangle A, B, and C, the vertices of the right angled triangle A, B, and C, but I would try to accustom yourself to not seeing that. All right, so I'm just for fun, I'm going to label this triangle, I'm going to label it D, oopsies, I'm going to label it D, E, F. All right, and now I'm going to go about this. So the first thing I'm going to do, the next thing I'm going to do is I'm going to locate my hypotenuse. Here's my right angle, and so that tells me that this side length H is my hypotenuse. And so now it's important, here's another thing that I forgot to mention, but that is probably good to mention, is that when you're indicating, when you're representing the symbols, representing the vertices of these triangles, the side opposite that angle will have the same letter, but only in lowercase. So for example, if I'm representing this angle right here in the lower left as uppercase D, then that means that the side length opposite it, which in this case is my hypotenuse, would be represented by lowercase d. And the same goes for the other side. So, the side opposite my F would be lowercase f. The side opposite this 8 here would be lowercase e. And so now I can symbolize the relationship between these three sides. I could use X if I wanted to. It doesn't really matter. All right, I'm going to carry on. Let me get rid of some of this. So this was F. So now when I look at this, I'm going to say, all right, well, D is my hypotenuse, so D squared is equal to. And I have this is F, and this was E, so F squared plus E squared. Now I'm going to just sub that in. So D I actually represented with X, so now is where I'm going to say, well, X squared. F was 6, so 6 squared plus 8 squared, and I'm just going to work that out. So 6 squared is 36, and 8 squared is 64. And so now I'm going to work that out clean this up a bit, that gives me 100. So you may remember that to undo a square, I take the square root. And so by square rooting something that is squared, I undo the square, and that simply gives me x. So whatever I do to one side, I'm going to do to my other side. So a little note about this is that, right here I can see that I'm going to end up with a nice whole number. Unfortunately, the value under the radical sign isn't always a number that has a perfect whole number square root. If it doesn't, my advice to you is to leave that value under the square root sign and just simply write it as a root answer, except if you're solving a word problem where you're looking at a measurement or where the value that you're solving for has meaning. That's where I would not do that. Okay, let's try another example. All right, so in this example here, I'm gonna label my sides as I don't know, randomly QRS. I just want us to practice this business of labeling them in an alternate way. Q, R, S. So that means that this side would be little s, this side with the 8 would be little r, and this side over where the y is would be little q. So I'm going to locate my hypotenuse. Here's my right angle. So my hypotenuse in this case is symbolized by the s. So I can go ahead and write out my equation. So s squared is equal to q squared plus r squared. Now I'm going to fill in the values that I have. So I have for s, the side length is 12, so I'm going to fill that in. So 12 squared is equal to, I don't know what q is, so I have the symbol y there, so y squared plus, and then r happens to be 8. So I'm going to square that as well. All right, and so now I'm going to clean this up a little bit, but you'll notice first off that the unknown side is not all on its own on one side of that equation. So that means that I'm going to need to do a little bit more algebra. I'm going to need to take an additional step. So 12 squared is 144 equals y squared plus, and then 8 squared is 64. So doing a little bit of math here, I know that I'm going to have 144 minus 64, and that's going to give me y squared. So 144 minus 64, let's just do that, 0 and then 8. So y squared ends up being 80. So this is like I was just saying to you, right? So I'm not done yet. And in fact, a lot of the mistakes when I see them have to do with people forgetting to take the square root of their answer in order to solve for the side length. So I still need to take the square root of each side here. And when I do that, I get that y is equal to some sort of decimal. So depending on the question, you may want to simply leave that as root 80, or you could write that as whatever the value of root 80 is. But I'm going to encourage you in non-word problems where the value of that side has no meaning to leave it as under the radical sign, under the root sign. All right, so finally, here that we're at the end of our Get Ready skills for this unit. Here are some additional homework questions relating to Pythagorean theorem that I would like you to work through. And if you have any questions, make sure that you jot them down and remind yourself to ask them on Monday when we get back together.